Hi, it's time for another math easy solution to discuss further into improper integrals and now go over the comparison theorem for type 1 improper integrals. Basically, sometimes evaluating an improper integral is either very difficult or even impossible to determine an exact value. In these cases, it is still important to know if the integral converges or diverges. In such cases, the following theorem is useful for type 1 improper integrals. So this one will deal with type 2 in a later video. Basically, so type 1, again, recall, it deals with infinite intervals. So here's the theorem. So the comparison theorem for type 1 improper integrals. Suppose that the functions f and g are both continuous functions, where f of x is always greater than g of x, and they're both greater than equal to 0 for the interval while x is greater than equal to a. So if we have the integral from a to infinity of f of x dx, if this is convergent, then so is the integral from a to infinity of g of x dx. So this is also convergent. So that's a theorem, and again, that's because f of x is always greater than g of x. So if it converges, this also converges, the integral of it. And likewise, if the integral from a to infinity of g of x, not f, so if g of x is divergent, then this means that the integral of a to infinity of f of x is divergent. That's because this is always greater than this integral. So if this integral is going to infinity, the integral or the area under the curve of f of x is also going to infinity. And similarly, for x is less than equal to a, if you look on the flip side, integral from negative infinity to a of f of x dx is convergent, then we have, so again, then the area under the curve of g of x dx is convergent, or the integral from negative infinity to a. And likewise, again, if this is divergent, this is divergent as well, because this is always greater than it. So to illustrate why this is true, let's just take a look when x is greater than or equal to a. So if we have the graph like this, xy curve, let's go at a here, this is x equals to a, and let's just draw a curve. Let's just draw a curve function like this, like f. So this is f of x. So now let's draw the curve g. So f of x is always greater than or equal to g right here. So it's always greater than it, and they're both greater than or equal to 0 in this case. So if we have something like this, as you could see here, this is our function g, and the area underneath, I'll just shade it in red. As you could see, in this case, I'm just making it just go small like that. And the area underneath the f of x function, I'll get this in blue. And so the area underneath the function f is blue and red, so it's the combination of the two. And as you can see visually, basically, if this area, so if area under, let's go f, is, so this blue and red is finite. So if it's finite, then basically the area underneath the g is finite. And then basically so is area under g, and you could just clearly see that this red is going to be always less than or equal to the area of the shaded region red and blue. So you're always this is just an extra region here. So as you can see, just visually, this has to be true for the first part A. So if this is convergent, then this is basically also convergent, or the area is finite. But likewise, if this area right here, if this is infinite, let's say if area under g is infinite, then basically so is the area under f, because f is, well, the area is greater than the area under g. Then so is so is the area, let's write the area under f. So this is just a visual representation of these two, and then similarly you could draw for these exact same things. These are just for the other side. So if you go to negative infinity to a, and for g of x, d of x. Yeah, and here for completeness sake, basically I just drew the exact same thing, type of example as this one here, but now we're dealing with going to negative infinity. So if x is always less than or equal to a, so you have something like this, and you could apply this basically the same principle, the same representation of area under the g is infinite, then so is the area under f. So area under here, if this is if the area under f is finite, then so is area under g, etc. So now that we covered the theorem, here's an important note about the theorem. The reverse of the theorem is not necessarily true. So basically, if we were to reverse it, instead said if the integral from a to infinity of g of x is convergent, then the integral from a to infinity of fx may or may not be convergent. I'll illustrate this soon. Basically, what this is saying, if this is convergent, because the number of fx is always greater than it, so fx could diverge as well. And again, if fx is divergent, then the integral from a to infinity of g of x dx may or may not be divergent, because we already know this is already greater than equal to g of x. So if this is going to infinity, for example, this one could still go to, well, converge and have a finite area. And similarly, the same is the case for when x is less than or equal to a. So basically the same thing here. I'm not going to go over that. I just put this for completeness sake. And this is the same thing we were dealing with negative infinity to a. So an example to show how this is not necessarily true is basically if we were to look at a function that looks something like this. This is how we can look at it. Let's go from this xy curve. Let's say you had a function, again this is a, and let's draw our function f such that it clearly diverges. So that's the function f. So as you can see, it is diverging, or this has an infinite area underneath. And now if we were to graph, let's just graph g of x where it has, let's say, a finite area. Let's just draw it where it's going down and down, and this is our g of x. So that's our g function. And again, if we were to shade in the area like this, and then shade this down for this area underneath the f, as you can see, the f, this one is, well, this is diverting, or it's going to be infinite area. Infinite area. And let's just assume again that underneath this g function is, let's say, a finite area. So this example, just drawing this out, shows that the reverse is not necessarily true. So in this case here, for example, if this function g of x is convergent, so in this case is finite area. So if it's finite area, this just means it's, well, converges right here. So the integral is converges, but then f of x may or may not be convergent, and in this case it's, well, divergent. So here is divergent, or diverges. So it clearly here is not convergent. So in this case it's divergent. And then if you go the other way around for part B, if this is divergent, which f of x is divergent, then g of x may or may not be divergent. In this case it converges, which is clearly shows that the reverse is not true in this case. So anyways, that's all for today. Hopefully you learned from this pretty useful basically a video on how to find if a function is improper integral of type 1 is divergent or convergent if you cannot solve that function easily. Anyways, all for today. Hopefully you learned, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.